Taking part in this briefing, we have Bernard Foing, who is the Senior Exploration Officer at the European Space Research and Technology Center of the European Space Agency, and is also the Executive Director of the International Lunar Exploration Working Group. Speaking after him, we have Dave Smith, who is the Grail Deputy Principal Investigator at the NASA Goddard Space Flight Center, and he's also affiliated with the MIT. Afterwards, we have Harald Hessinger, who is a professor at the Institute of Planetology at the University of Münster in Germany. And finally, we have James Head, who is a professor of geological sciences at Brown University in the US.
So, welcome to the moon. Please fasten your seatbelt. We are going to unveil you a new face of the moon. The theme of EGU is the face of the Earth, so we thought it would be an interesting theme. So we had this morning a very interesting session of lunar science and exploration, where we have heard some new results from missions, but also some legacy from previous missions. So I am going to talk on a special event today. This year we are celebrating the 10 years after launch of SmartOne. 10 years ago we were still on our way to the moon. And I will just present to you some top 10 first and 10 years legacy. And we look also how we have engaged in a new fleet of lunar orbiters in the last decade. And now we are entering a new decade with surface missions on a way to human exploration in international lunar bases. So that's the top 10 first for the 10 years that I've mentioned. SmartOne was the first small mission for advanced research in technology, also developed in a very short time. We were the first mission to leave the Earth using solar power, the most fuel-effective mission, 60 liters of fuel to go to the moon, and the first demonstration of new technologies at the moon. Also, these were the first European views of the lunar poles and the far side, and with global coverage. And we heard already this morning some new results from these data that are still being analyzed. This was the first infrared spectrometer around the moon, and we had also an X-ray fluorescence spectrometer measuring the elemental composition of the lunar surface. And with this technology mission, we developed an opportunity for scientists to make studies of the lunar geochemistry, geology, mineralogy, and precursor studies for exploration. So our motto was "Fly me to the moon." It was a very long travel to go there. About 10 years ago, we delivered this picture of Europe on our way to the moon. We are not yet arrived, and so you can recognize the Vienna on this picture. And we eventually arrived to the moon, and we had 18 months of lunar science measurements, and then we concluded the mission with a controlled grazing impact on the surface of the moon that was observed from the Earth. So that's one of another first. And also this mission was a first in this decade, opening a series of exchange with other space agencies, scientists within the International Lunar Group, and where also we have seen a strong interest of the public, of the youth, to engage in lunar mission and lunar exploration. And in practice, we also use some of the collaborations started with SmartOne to put instruments on board Chandrayaan-1, 3 instruments from ESA, but also we collaborated with the Chinese on their mission, Chang'e-1, 2, and the latest, Chang'e-3. So SmartOne was a mission that developed technologies that are now also being pushed further in a mission, BP Colombo, for instance, that we are preparing to go to Mercury, but also the technology of ion propulsion as applications. Now we are developing new launchers, low cost, that are going to send telecom satellites that will use solitary propulsion. And SmartOne was in fact the first satellite to demonstrate some of these technologies to navigate. And we had a number of sensors that we were having on board, very miniaturized, that have also been developed further for future missions. The face of the moon, that's the theme of EGU. We have looked at it with a SmartOne. We have looked at the wrinkles of the moon. We have looked of the imperfections due to the impact on the surface of the moon. We have looked at the veins on the face of the moon. That's, you could say that a volcano bring magma to the surface. And so that's a way we have studied the face of the moon as a way to understand what is shaping rocky planets. And we had a special new perspective on polar regions and created even our own impact that with a controlled descent and grazing on the surface. So here's a view of some of these lava tubes and a reel, so you can have what is left of a lava river. And you can see here how we try to put this in perspective with previous surface exploration as conducted by Apollo 15 astronauts, or even with explorers 400 years ago, Galileo making the first telescopic image of the moon. We took advantage of a series of images during the whole year of the South Pole to deliver a mosaic of the South Pole, a kind of each guide map that you could use when you go to travel there. Now this has been replaced by much better maps that will be described by my LRO colleagues. But eventually, we could confirm that close to the south pole of the moon, there is a place which is in almost permanent sunlight. So if you would want to deploy a lander which could live only on solar power, that would be the place to go. So as I mentioned, eventually, we ended the mission with a controlled grazing impact because we had no fuel left, but we were able to direct the spacecraft to the surface within 2 seconds of predictions, and we were able to schedule observation from Earth to study not only the flash, but also the cloud of debris that were projected there. So one of our questions was, where is the SmartOne impact? And recently, making use of the information on the timing that we had, we have looked at LRO data to search for the SmartOne impact. And this is a candidate place where we believe it is. So we have just presented that this morning at EGU. So for the future, we look how this fleet of precursor orbiters around the moon can prepare to the next step, surface landers that could be working in coordination as part of a robotic village, and then in placing infrastructures and preparing for a permanent human outpost. So we have looked also with SmartOne how to combine the data with the latest mission like LRO or Kaguya. In particular, we were very interested in lava tube and skylight. We were discovered by Kaguya, and we have analyzed some of that. We even on Earth made some ground simulation of what it could be to explore in this lava tube. That would be for a more later step. And thanks to the we invited some scientists from all over the world to contribute to SmartOne data analysis and operation. And this was an opportunity for us to collaborate with the Chinese that made use of SmartOne around the moon to test their ground stations. And then they invited us to collaborate on using ESA ground station to download the data from Chang'e 1, Chang'e 2. Chang'e 2 would, by the way, you see the first map of Chang'e 2 unveiled by the Prime Minister of China, which is something also we would target to do in Europe, get a strong interest from our politicians into lunar science and exploration, and even Chang'e 3, where ESA has provided ground station and support at critical moment during the insertion and the landing of the Chang'e 3 lander and the U2 rover. U2 rover now is opening the next decade of mission on the surface of the moon, and there are a number of projects which are currently under work from government. So in China, we are looking also at collaboration with Roscosmos, the Russian Space Agency, on the Lunar Globe Lunar Resource Program, and we are also looking at the commercial lunar missions that are now on preparation. So the next decade will be certainly very exciting to continue the exploitation of data from orbiters, but also to explore the surface. Thank you very much. So now we go to the next presentation from Dr. Dave Smith from MIT and the Goddard Space Flight Center on some latest news and status report on the Lunar Reconnaissance Orbiter.
Well, thank you. I'd like to tell you a little bit about the Lunar Reconnaissance Orbiter mission and kind of what's been exciting in the last 6 months or so. And there are many things, but unfortunately can only choose a couple of them. LRO has been orbiting the moon now successfully for 10 years. Sorry, 5 years. Started in 2009. And we've had 5-year anniversary, and all the instruments are working almost completely as one, an experimental one, which is not fully operational. Otherwise, all the others are collecting data. So after 5 years, we have amassed a considerable amount of data. And I'm not going to be able to show you, I'm not going to show you any images, but you know, images have been one of the major features associated with the mission in terms of the very high resolution 50-centimeter camera kind of images that are taken of everything from the footprints of the astronauts and the locations and of the landers, etc., on the surface of the moon. But what I'd like to talk about today, I think, is just for a few minutes, is a thing that's been interesting for many of us for a while, is this question of the poles of the moon, and in particular the South Pole, and the possibility of water ice in the poles there. And there's been a lot of discussion about this. It hasn't yet finally converged by any means, but I think it's fair to say that we're beginning to understand the observations better now than we did even 3 or 4 years ago. And so the chart that I've put on the screen there, for example, is in fact one that brings together two instruments. One that is measuring, a laser altimeter is measuring literally the brightness of the surface. So it sends a laser pulse to the surface. It measures the energy coming back, and it essentially gets the albedo at this wavelength of 1064 nanometers. And we have that across all of the planet, of course, but we're particularly interested in the polar regions, because the suspicion is and belief is that you know, when ice is there, it'll be a brighter surface than when it's what we call the normal regolith. And so we've been collecting these data, and another instrument called Diviner has been measuring the temperature of the surface. And so we have kind of put together recently, see how the temperatures are matching up with what we think of the brightness of the surface as seen by the laser altimeter. And the uniqueness of the laser altimeter is it's what we call something like a normal albedo, which means it's straight down and straight up. There's no reflected sunlight or anything of that kind. This generates its own radiation and catches the photons as they come back. And on the right-hand chart there, you'll see a map of the temperatures, the big green chart there, of the South Pole. In the middle there is Shoemaker, the big crater right in the middle, which is the dark blue, dark red colors in there. And those dark red, dark blue colors are the areas which are in permanent shadow. In other words, the sunlight never gets in there. It might get in through reflection off a mountain on the edge or something like this of the crater, but generally speaking, it's in permanent shadow. And it's probably been that way for maybe 1 or 2 billion years. We don't really know. The craters are old, and as far as we know, no sunlight has got in there. Now, the colors on there tell you that, in fact, those temperatures are 20 to 30 degrees, maybe 40 degrees above absolute zero. Probably the lowest temperatures we actually measured anywhere in the solar system. It's a little surprising that we'll be on our moon, but at the moment that apparently is the case. And so what Dave Page, the principal investigator of the Diviner instrument, he's taking the albedo measurements that we got from the laser altimeter, and they're down in the bottom left-hand corner there. All those red and blue dots are in fact brightness measurements, and so the brightness is on the left-hand side, going from the bottom to the top, and on the bottom it goes the temperature. It goes from 0 Kelvin to I think it's about 300 degrees there. And the point about this is not so much the actual shape and or where the points are in direct themselves, but the fact that those that are now in red, they've been highlighted, but at the very low end, below 100 degrees Kelvin, there's a sudden increase in the brightness as seen by the laser altimeter at 1064 nanometers. It's a micron. Okay, so all of a sudden we see this change, and we thought, well, I think it makes sense that, in fact, as it gets very colder, if there's any way that the very thin moisture that must exist up there could land on the surface and freeze, then it would look up a little brighter. What Dave Page has managed to show also is that those actually doesn't occur all the time. It occurs at certain times. And the red indicates that, in fact, all those red ones are actually in at nighttime when it's dark. And when you move to the blue, although it's not actually in sunlight, it's actually getting some light coming from reflected from the sky and such like there. So that if you took away the red, which was at the nighttime, it wouldn't look particularly spectacular in that region. But the nighttime ones show it is. So to us, this is saying that there is a cycle of some kind. Almost certainly, but not proof that it's water vapor on the surface that's frozen. It's probably a few microns thick. It looks as if when the temperatures rise, for whatever reason, during the right part of the day, the water vapor or whatever it is disappears, and that we would expect to occur around 100, 140 degrees Kelvin, and you can see on there that it is. So we're suspicious, in fact, if not pretty confident, that what we're seeing now is evidence of water vapor condensing in the craters of the North Pole, in the shadowed areas, only in those blue and the red areas that you see on the map there, that indicate that when it's cold in those permanently dark areas, then ice forms. And then when, for some reason or other, as the surrounding area gets warmed up by some sunlight, then the very thin layer of H2O, as we think it is, it disappears and comes back again in the night. So it's probably a 30-day cycle in the course of a day. Okay, could I have the next chart? Yeah, next chart. It looks at this looks at something very similar. We have another instrument on LRO. This is from Russia. It's the LEND instrument. It measures neutron detections on the surface. And the thing about neutrons is that if you get instead of getting a normal background of neutrons looking at the surface, but in fact you lose the neutrons, you get a depression in the neutrons, then it's an indication that that somewhere in there is hydrogen, and the expectation is that hydrogen is bonded with water. It could be bonded with other things, but most likely it's with water. And so there is a hydrogen map, if you like, of water that suggests maybe in places there's a few percent by weight of water in the top meter of the surface. It gets down that low. The laser altimeter does a micron at the surface, and this instrument goes down to about a meter. The interesting part about this now, which has occurred in the last 6 months, is that when we look at those neutron results now as a function of local time, and this has only come about recently since we've got a more balanced data set right now for this, actually for all of the instruments, though actually we're seeing an increase in the absorption of neutrons in the early hours of the morning between 0 and 6, and then at about what I might call sunrise, it starts to increase, which means that whatever water vapor in that top meter is less, at least. Okay, and then it continues that way, and when the sun starts to set, if I can put it that way, it starts to get cold again, then the water vapor, well, I should say the hydrogen appears to increase in that. We believe it's attached to oxygen and becomes water. Now, this is, to me, is a little unusual, because we usually think that 10 centimeters below the surface that the temperature doesn't change very much. It's insulated by a dry layer over the surface of the crust. Actually, this is suggesting, and we heard this morning in one of the papers from the Russians actually, that there's evidence that they think that the layer of dry material above this area is maybe 5-10 centimeters deep, a little less than we expected. But the neutrons can only be detected down to about a meter. So all this variation that we're seeing here now is happening within the top tens of centimeters. It, in a sense, corroborates what we're seeing in the top micron of the surface. Different feature and a different kind of phenomenon in a sense, but it looks as if we're seeing variable water in the top meter of the lunar crust in the south polar region. And the next chart, the last one I'd like to show you, is rather different. It brings together two of the missions in some senses. Now, this brings together the Grail mission, which has measured the gravity field of the moon, and it brings together if I might put it this way, the geology that we're getting from LRO. And this picture shows a series of mascons, the big red blobs in the middle of the picture there on the near side of the moon. Those are gravity anomalies. In other words, that indicates a mass, because they're red, a mass excess. So we've removed craters and things of that kind from topography. We know how to do that. And now we're looking at the anomalous mass on the surface of the moon, or within the top few hundred kilometers. Okay. Now, the white lines we get from imaging and other sources as well, which are regions that are called wrinkle ridges or extensional graben, which are distortions of the surface, only maybe a few hundred meters high, but quite extensive in length. And now we're seeing not only do these white lines that you see on there fitting right inside or on top of the red gravity anomalies, and it's suggesting very strongly to us that these features, which are either contractional or expansion, as the case may be, have been formed as a result of the cooling of the material that is now making up that mass anomaly there. So some kind of contraction or otherwise has taken place, which would cause the surface to wrinkle and create these what I'm looking specifically at the white lines, and not just on the mascons. They're frequently in places where we have reddish areas. Okay, and so we're now beginning to tie together what we would see as a geological feature with the actual mass of the area, and how that could have in itself created the features that we're seeing by almost certainly some level of contraction as the material cooled a long time ago, a couple of billion years ago, maybe more. And so this is an outcome of two missions, LRO and the Grail mission that was at the moon until a year or so ago, and provided a really spectacular gravity model for the planet, which enabled us to start saying something about where the mass is distributed on the surface of the moon and to some degree internally to the moon. And we brought them kind of together here in this early result. And so this is the kind of work that LRO wants to do in what we're calling a second extended mission that would start about October 1. It's already done 5 years. It will hopefully we'll be able to go another 2 years. There's enough fuel on spacecraft to do another 5 or 6 years, but that's a long time away, and something can go wrong between now and then. But otherwise, the spacecraft's doing very well. Thank you.
Good. Thank you, Dave. So, as you can see, a new face of the moon with some volatiles, with some wrinkles, putting a bit of weight in some places. And so we have, but see, a lot of new science results on the moon. The next speaker is Professor Harry Isinger. Let's see. And from Münster University, Institute of Planetary Geology. So,
okay, let me just start off why you should care about the moon. Okay, for us in planetology, the moon is probably the single most important object in our solar system, not only to understand the moon and the Earth-Moon system, but also to understand the entire solar system. So there are some people out there that argue, well, we've been to the moon, we had 12 astronauts walking on the surface of the moon, so we've been there, we've done that. And let me just assure you that this is just wrong. Okay, we have in fact numerous questions that are unsolved and that are of key importance for understanding the rest of the solar system. So right now we are in a really lucky situation that we have or had in the last couple of years numerous missions that visited the moon, and so we learned a lot, and I'm going to show you at least a couple of results specifically from the LROC camera, the Lunar Reconnaissance Orbiter camera, and yeah, that's going to be hopefully exciting for you. For us, let me just explain why the moon is so important for us. It's really because the moon is like a history book, okay? So we can look back into the early times of the solar system. We can study the early history and evolution of the solar system and the Earth-Moon system by investigating and studying the moon in detail. So in addition to that, the moon has no atmosphere, it has no moving plates, no plate tectonics, has no life as far as we know. And so in this respect, the moon allows us really to study geologic processes in their purest form. And so this is sort of then the introduction also to Jim's talk, who is going to talk much more about geology and what we try to accomplish on the moon in this respect. Next, please. So let me just give you some highlights of the camera that I was working with for the last 5 years. Very recently we put together the largest image ever. Okay, it's called the Gigapan, and it shows the moon from about 60 degrees north all the way up to the North Pole at 2-meter resolution. So this is already downsampled data quality, believe it or not, but LRO is taking pictures as good as 0.5 meter per pixel resolution. So we are about 50 kilometers above the surface of the moon, looking straight down, and we would certainly recognize each individual chair in this room here with our camera. So, and yeah, we created the greatest picture. It's on the web. You can just Google it, go to Gigapan, and you can scroll around it, and just be careful. It's easy to get totally lost in this picture. You can scroll around for hours. Okay, I've done this, but it's fantastic. All right. So then, of course, with this great resolution, we can study the landing sites. We see all the equipment that is brought back. We see the footprints. We see the American flag, at least the shadow of it. So why is this important? Well, because the astronauts left behind some laser reflectors, and so by shooting lasers to these points and exactly hitting them, we can sort of measure the distance between the moon and Earth, and we can learn something about the internal distribution of mass and the libration of the moon. Dave was already alluding to this. The illumination at the poles is of key importance for us. So we're observing the moon now for 5 years, and we're producing illumination maps every month. Okay, we have global maps just to study how the shades or the shadow and the permanently illuminated areas change. Reason for that is that if you want to have a lunar outpost, you need a reliable source of power, and if you know where the sun is basically always shining on the moon, then you could put up some solar panels and you could have your lunar base there basically, and you would not have to worry about power. I'm going to talk a little bit more in detail about the validation of the chronology. So how do we actually learn about the ages of the surfaces on the moon and what the implications for the rest of the solar system are. Dave was already talking about some shrinking of the moon. By looking at these high resolution images, we learned that the moon was probably shrinking in diameter by about 100 meters over the last 1 billion years at least. Okay, so it might have shrunk a little more. We're still working on this. The discovery of Lunar Cataclysm, it's one of the Russian rovers, was also a big hit because it was lost since the 70s. We didn't know where the Russians parked this car, okay, but we found it in our data. And again, this is really important because this rover also has a laser reflector, but it's far away from the Apollo landing site, so it gives us a much better idea of the libration of the moon, how the moon wobbles basically, and how the mass in its interior is distributed. Another surprise was that we discovered some very unusual volcanic construct, the so-called Compton-Belkovich construct, and this is very silicic volcanism, so much more evolved, much more silica-rich than the usual black spots that you see with your naked eyes. Those are basaltic rocks, volcanic rocks, but those at Compton-Belkovich are definitely compositionally very, very different. And I've talked about the lava tube skylights again. This is a great discovery because eventually we could use such lava tubes. They are basically caves, okay, as potential habitats for lunar outposts. And then, of course, we are also interested in determining how frequently the moon actually gets bombarded with asteroids and projectiles, if you will. And so we now have images that we can compare either with Apollo data that were taken 40 or 50 years ago, but also within the time frame of our mission. Within 5 years, we see differences. We see fresh craters that formed while our spacecraft was in orbit around the moon. And that's not a rare observation. In fact, we discovered thousands, and Emerson Spira talked about this earlier today. And of course, we can confirm that the Chinese really landed on the moon. We saw the area before they landed, and we saw the area after they touched down, and sure enough, we see the spacecraft and the U2 rover. So that's good news. So there is no discussion whether China ever landed on the moon, you know, so we know that for sure. Next, please. So let me just focus now a little bit on the chronology. How this works is very simple. You can just imagine this fresh surface being exposed to the meteorite bombardment. So if you have a short time of exposure, you will have only a small number of impact craters. The longer you expose this surface, the more impact craters you will get on the surface. And we can, by just simply counting those craters, we can figure out which surface on the moon is of a certain age. Next, please. So we can then use the radiometric ages of the returned samples from the lunar data, lunar missions or the Apollo missions. So radiometric ages are those that you determine in the laboratory, and we can combine our crater statistics with the absolute age of these samples, and what you get is sort of a curve like you see on the slide here. Doesn't look very spectacular, but let me assure you this is a very important curve because it not only allows us to date areas on the moon that have not been visited by astronauts, but we also extrapolate this curve to any other planet in our solar system. So the message here is, if we don't get it right here on the moon, we will propagate this error and we will date all surfaces in our solar system incorrectly. Okay, so understanding the chronology of the moon is really of utmost importance. And you can see some data points do not really match, or did not really match the curve. Recent work that I did was to investigate these areas, and we sort of could validate this curve. But you also see that there are only 4 data points for very young ages, okay, and basically no data points beyond, let's say, about 4 billion years. So we definitely have gaps in our knowledge, and we need to understand this. We need to get samples back from those young areas and those very old areas. Otherwise, we are sort of not completely understand this chronology. Next, please. So I just mentioned the old ages. This is a crater count that I did for the oldest and largest impact structure on the moon. It's called the South Pole Aitken Basin. And what you can see here is that the basin is about 4.26 billion years old, at least according to my counts. Okay, there is some debate about this because it's very challenging to do these counts. Other groups have different opinions, but if you assume, or if you take this age of about 4.2 or 4.3 billion years now, it's really an important date because it relates to what we call the Lunar Cataclysm. Next, please. So, what the Lunar Cataclysm is an idea that comes back from the Apollo radiometric ages, where people argued that at about 3.9 to 4 billion years, the moon was exceptionally bombarded with large projectiles that formed basins and so forth. So you see the spike in the red curve. That's one idea. Another group has sort of the idea of a more continuous decline. That's the black curve. And testing this idea is really important because if we really had the spike 3.9 billion years, and when it ends, that's about the first time that we see life here on Earth. So there's this word of impact frustration. So one idea is that once the impact rate declined, you could actually have then life evolve on the planet Earth here. Okay, so testing this idea is really important. How does this relate to the South Pole Aitken Basin? Well, if South Pole Aitken Basin would have been at about 4 billion years, it would sort of be consistent with this cataclysm idea, but now that it's much older, I would argue that the cataclysm is not that well supported by my data at all. If you look at some meteorites that come from the moon, you can see the age distribution there in these two different studies by Cohen et al. In 2008 and Neukom et al. 2012, and you see this very broad range of ages. There is basically no spike, and so again, those data would also argue that the cataclysm is probably not real, but was a sampling bias from the Apollo missions. And with that, I hand over to Jim, who's going to talk much more about geology. Thank you.
Okay, thank you, Harry. So the next speaker is Professor Jim Head from Brown University. He had also a long experience working with Apollo astronauts, training them. So he gives us some latest geology results, but also some perspective on future human exploration. Jim?
Thank you very much, Bernard. It's really a great pleasure to be here, because it's such an exciting time in lunar and planetary science. In particular, lunar science is really representing the cornerstone, a keystone of our understanding of the rest of the planets. You can see from this image that the moon is, of course, very close. In the central part of the image, you can see a picture taken from the International Space Station above the glow of the horizon of the atmosphere, and you can see the moon in the background. And of course, it's very obvious, having inspired scientists and people for generations just looking up in the sky. Next, please. What I want to focus on is the fact that we know so much about the moon that, in fact, it is a fundamental cornerstone to understanding the rest of the terrestrial planets. We have spacecraft in orbit around other planetary bodies, and we're getting tremendous amounts of information, giving us insight into these bodies, the Moon, Mercury, Mars, Venus, and so on. And yet, at the same time, our level of knowledge is fairly primitive compared to what we know about the Moon. The Moon is arguably the most well-understood planetary body other than the Earth. And you may say, well, why should we go back if that's the case? The answer is because we can ask extremely sophisticated and important questions about the moon that we can't ask of these other planetary bodies and won't be able to ask for many years to come because we won't have the information. So in-depth exploration of the moon must accompany our quest to understand our own home planet and the other planets in the solar system. And fortunately, we have a lot of capability to be able to do that. Shown here are a series of missions over the last 57 years, and you can in fact see that there's been a renaissance on the lower right-hand corner in the last decade, which has provided us with tremendous information about the global characteristics of the planet, as you heard from Dave Smith and Harry Hiesinger. Next, please. Now, a key point is, where do we go? What do we do? What kind of robotic missions, what kind of human exploration missions should we send to the moon to take advantage of this wealth of information to address these fundamental questions we couldn't address on other planetary bodies? Recently, earlier this year in March, we in fact held a Microsymposium 55, the title of which was Scientific Destinations for Human Exploration. And as you can see from the poster here for that mission, for that meeting, in fact, the moon figured prominently. It's the large white thing in the front there. There are also other human destinations, but a lot of emphasis was placed on the exciting questions we could address with future human and robotic exploration of the moon. You can see in the upper left-hand corner there a picture of an astronaut on the surface. That's Apollo 15 Commander David Scott. David Scott and Jack Schmitt, next slide please, were both in attendance at this meeting and gave personal perspectives on their exploration of the moon as well as future plans for the moon. So in fact, we spent a whole day talking about what we can find out from the moon from future exploration, both human and robotic. Indeed, Carly Peters, Sasha Basilevsky, and others talked about these major questions that could be addressed. Jack Schmitt, the Apollo 17 lunar module pilot, and Dave Scott, the Apollo 15 commander, discussed not only where they'd been, what they did, but how it can be improved in the future. And that's one of the things I really want to touch on. Other people discussed the young people, the last part of the agenda there. Wonderful young people talking about their dreams for the future. And in fact, the moon is the destination for human and robotic exploration for many of the people in the young scientist group, if you will. Next, please. This is a series of questions that, in fact, were addressed and raised at the microsymposium, as well as in other documents that have been referred to throughout this discussion, and they're very, very fundamental. The origin of the moon, early bombardment history, internal thermal evolution, all things we can address in detail because we have this framework of information from these earlier missions. Many of these things, for example, the detailed structure of the crust, are not able to be determined for Mars for the foreseeable future. We're sending a spacecraft to the surface of Mars called the InSight mission, which will try to get the detailed structure of one area of the crust of Mars. On the moon, we have many seismometers from the past. We have orbital gravity data. We have all sorts of things that are providing us with much, much better insight, and we can address questions in much more detail. But how do we go about doing this? Next slide, please. One of the things we've learned, both from all these missions, and in particular from Apollo, as a participant in Apollo, I must tell you that it was an amazing experience to work together with the scientists and engineers and the operations people to really develop what was known as science and engineering synergism, where we get the engineers and the scientists together at the beginning and we optimize the planning for the future. This pays off with immense dividends, and because of the missions we've had from China, from Japan, from European Space Agency, from India, from the US, from Russia, all over the planet, these countries or entities have sent missions to the moon, and the results of these have really proven to be something that we all work together, as Bernard described, to interpret. So we can work together in the future, and we're starting to do this, working together with international scientists, engineers, to plan these future missions. You can see in the graphic in the upper left-hand corner there that all the Apollo missions have been plotted at a common point, and you can see how far they were able to traverse out away from the surface, away from the landing point, out to 14, 15 or so kilometers. The red line in the lower part is Lunar, which landed on the moon, the Russian rover, and traversed more than that 40 years ago. Okay, so we know we can traverse the moon like this. We have all kinds of operations experience. We have all kinds of spacecraft experience, team experience, etc. In the upper part, the line extending all the way across the diagram there is in fact the traverses, the links of the traverses from the two Mars exploration rovers which have been on the moon for a decade. Okay, so we know how to do this. We have the capabilities, we have the fundamental questions, and we can in fact work to introduce an international program of human and robotic exploration. And indeed, human exploration, you might say, well, we can't do that because it's too expensive. I think one really needs to think back and think through that statement, as has been done, last slide please, from, in fact, a group at Massachusetts Institute of Technology and Brown University. These scientists and engineers working together from the bottom-up process asked the question, how can we send humans back to the moon at an affordable rate? What they did was they said, first, very logical students, what's worked in the past? How can we build on something that worked? Well, Apollo worked. So they started with a fundamental Apollo architecture and asked the question, what can 40 plus years of technological development do to help us increase the up mass, what you take to the moon, increase the down mass, the rocks you bring back, and increase the capabilities on the moon. And these remarkable young engineers from MIT, working together with scientists from Brown, found, in fact, that you could take, in fact, have a duration of 7 days as opposed to the Apollo 3 days, a surface mobility with 2 rovers, and, in fact, equatorial, going from just equatorial capabilities on the near side to actually getting 100% access to the moon, could land on the far side, and sample returns would increased by 3.5 times. So this is really amazing. The point is that new technologies can take an old idea and design and do incredible amounts for a lot less money. So I would just close by saying the moon is really the keystone, the cornerstone for future exploration of the planetary bodies to get a scientific understanding of a lot of the things we're seeing and the missing chapters in Earth history. We know how to do it. We've done it before. We have a bunch of very excited young people from all over the world engaged in making this happen in the future, and it can be done. Thank you.
Okay, thank you. So you see a scientific perspective, a technical developments, but also the moon as a platform that can inspire innovation, new solution, and also that could create job opportunities for our economies. So that's also how we see that the scientists have to support lunar exploration projects which are even bigger than what science alone could achieve. So thank you.
We have time for one or two short questions, if there are any.
Obviously, there's an awful lot that can be done in terms of lunar exploration, but if you had to pick one direction we should go in from now on, if money, is quite limited and we need to focus our research into one region of all that you've just presented here, what would that be?
Yeah, so from my perspective, at the phase where we are now, we have done the fleet of orbiters. The next step is to deploy some measurement on the surface with the landers, and there are a few of those landers that are being developed, but also with a long-term vision that would lead to return sample and then later have humans, and each time learning from the previous phase to do it in a cost-effective manner, but also in a lower risk, and making it affordable. I don't know if you have other perspectives on that?
Yeah, I think if we're going to go back to the moon, we're eventually going to have to live off the land, if I might put it that way. And this is some of the emphasis associated with looking for water at the poles. It's not likely to be significant anywhere else, and may not be significant at the poles. But I think we need to go back and land there with the right equipment, and that may not be the first lander, but that can actually do enough on the surface to know whether the resources that a lot of people are talking about there that could be used to survive on are in fact actually there. Because if they're not there, and we have to take every drop of water, every ice cube to the moon to survive, it's going to be a tough journey.
Oh, you need good recycling technology as well, which is we are developing on the International Space Station. So some sustainable system which are needed to go further in deep space exploration, but also will have application on Earth. And Jim or Harry?
Well, for me, I think the next step would be sample return, because samples are a gift that keeps giving in a sense. So once you have it on Earth, you can study it now and you can study it in 50 years from now. And we just had a case where a study was done at green glasses from Apollo 15, performed by Alberto Sal from Brown University, that actually discovered water in those glasses. And this was possible because we now have so much better analytical techniques that were not available 40 or 50 years ago. So this is a good example, and samples teach us a lot what went on the moon, and that's crucially important to me.
I think it's a very good question, of course, and we all dream about having unlimited resources, but we have to be realistic about this. I think it's really important for there to be a significant amount of international cooperation, because it is a bit wasteful to be doing the same thing repeatedly. So far, we haven't really had that problem. For example, China plans to return samples from the moon. I hope ESA as well, and Russia certainly plans to return samples from the moon. Clearly, they're not going to go to the same place and pick up the same rock, so the more the merrier. The more people that can bring back samples, there's plenty of places to go. But I think it's critically important to work very closely towards international cooperation and collaboration. There are many bodies now that talk about this. Bernard is among the leaders in that area. I work in the field in Antarctica, and I've been to 5 seasons in Antarctica, and the international cooperation is amazing. It's essentially not a development area by international treaty. as the moon is as well. And so people very closely coordinate their national activity. Sometimes I'll fly there on a New Zealand aircraft, for example, or get a New Zealand helicopter ride because the resources are shared, etc. So I think that's something that we should very definitely look into. There's very little insight to infrastructure right now. Infrastructure is a funny word, but it's why the lights are on here today. It's why there's drinking water. It's invisible, but it's absolutely essential. We need to develop that for the moon. That's something that can be done internationally to free up people to fly the missions they want without having to take everything with them, for example, like communications equipment, etc. So there's lots that can be done internationally to reduce costs, and I hope that based on our success in Antarctica, that the same approach will be used on the moon and beyond.
Thank you. Are there any other questions? Okay, we'll actually need to finish now. If there are no other questions, I'll thank everyone for coming. Thank you very much for your
In case you are
contributions.
welcome to attend our session on the Friday morning on the future lunar exploration. We'll have some presentation of some of the ongoing project on the way toward this robotic village and this research base, which Antarctica is a great example of, for instance, what we could have a lunar research base with some international deployment of some infrastructure before to make it even more sustainable and give even more return to Earth.
Thank you. And while we are on the subject of advertising session, I'll advertise the next press conference tomorrow, which is on applying geosciences to crops, coffee, forensics, and wine, and it starts at 10. And we are done here at the Press Center, done for the day, but there are other interesting sessions you may be interested in attending this afternoon, including the IPCC Union session and a great debate on mining. Thank you.
Good.